Alright, so what I wanted to do for this demo is to begin by showing off this complex number library, which you can import and use in your QBJS programs, and comes with a decent handful of features to start with. So just in case, I'm gonna have our ruloscope open as well as our atlas of branchial space. And so let's begin. So without any bullshit philosophizing, a complex number is just an array with two elements on which you can perform functions and operations which preserve some kind of algebraic convenience. And this whole thing about negative numbers or rotations by 90 degrees, really don't have to think about it. So this library comes as a BAS file, which you can import with a line, and it gives you a kind of a namespace. And it comes with almost everything you might need, anywhere from creating a complex number, basic arithmetic, magnitude, phase, and of course logarithm and exponentiation. And you can see there the library is self-referential. Then you get some trigonometry, and then the crown jewel is the fast Fourier transform. And instead of jacking it from some 1980s magazine which is expanded to all fuck and over optimized, you can actually interact with the complex arithmetic in this function. And lastly, we have a bunch of so-called heat maps, visualization functions, which I'm about to show. Of course, the obligatory example is going to be this one. And you can already guess what this is. But in here you have the freedom to perform any complex operations you want without expanding them. For example, you'd probably read something that this is shit, it just turned into an arrow. Something like this. Here we're creating RC from our centered and scaled and flipped basic coordinates. Then we perform the recursive iteration, and here you see are using a multiplication to perform the exponent, but of course you can just as easily do something like this. C dot pow 2 0, and if everything is correct, nothing should change, right? So here we're performing this operation. Here we're performing this operation. And finally, this is the so-called escape time or bailout condition. Something like this. And as a stress test, you can change this exponent to a cubic or a cubic, yeah, and see the cubic Mandelbrot, the quartic Mandelbrot, And if you want to get fancy, you can even use a complex exponent. It should introduce a bunch of branch cuts everywhere and not going to be very attractive. Who gives a fuck here? Okay, whatever. Back to reality. And so that's your obligatory complex number library example. And here you can see the heat map or the visualization function being applied. So now let's try some of the other samples of the heat maps. Here we see the mapping of nothing more than a face portraiture of this function. We can try the contouring heat map as so, and get a Cartesian grid as well as a polar grid as so. Next we have the exponential function, and again, as you may remember, a complex exponential converts Cartesian to polar and vice versa. So here is the polar version, which matches with the top heat map. Convert it to Cartesian and you get a square grid. The next one is the trigonometric function, presumably sine right here, and it's just going to show you all the different heat maps. You have the red, green, blue, yellow, red, green, blue, polar checkerboard, and a Cartesian checkerboard. And then of course the next one is the M set, which you've already seen. And the final demonstration in the gallery is the fast Fourier transform. Pretty straightforward. You have two frequencies represented by a sum of sine waves. You take a Fourier transform and you see two distinct peaks, and this of course is a symmetrical reflection, which you can get into deeper. And it wouldn't be a demo if we don't try the inverse. And because this is colored in green and everything works correctly, this gray wave should just turn green, and it does. And finally, so-called filtering example, where we try to remove this peak by zeroing out these values in the frequency domain and taking the inverse, and we get this, which looks correct. You comment this out and you get back presumably something approximating this one. So that's that for the library. We also have some useful constants defined like 0, 1, I, and E. And so, okay. So the next thing I'm gonna try to do is create some kind of I don't know, screensaver, vector field, complex vector field, whatever you want to call it. And we'll start by removing all this useless garbage which we don't need. Like that. So that now it resembles more like a basic program. Import a library, set constants, create a graphical screen, define some, instantiate some variables, remove this shit. Fill the entire screen with pixels. And we'll start with the polar grid. So what I want to do is make something of a dipolar vector field. Something like this. Z minus 1 divided by Z plus 1 scale to whatever. So what are we going to do here? Simply W equals cdiv. Have our numerator, denominator. Our numerator can be Z to start and Z plus 1. Of course we want W. And already things are working. Let's zoom in a bit. Yeah, that looks fair enough. What happens if we change this to 2? Okay, this is a start. So what we have here is something of a magnetic dipole, I guess, or even 2 electrons next to each other. And in order to make use of this complex numbers library, we want to make some kind of a crowd pleaser screensaver, given all this insight into the branchial space of electromagnetic fields. Okay, so we have this drawn, and once again we're going to introduce a game loop. Limited down to 30 frames per second, and on every frame let's print the mouse coordinates. Here they are. Everything works fine. So then we convert our mouse coordinates into math coordinates by recycling this little transformation. And if I go near the origin, well, it doesn't get cleared, but you get the idea. So here, again, I'm going to copy this very transformation. And now, instead of printing X and Y, let's draw a circle at it. X and Y. Mm. 10. Okay, so annoyingly, we don't have this looking like a proper animation. So very quickly, I'm just gonna make a graphical page, draw this on, and use it as our background. Only since this is a visualization or a heat map, we don't really care what it does or whatever until later. And then we're just gonna turn it into a background wallpaper. Okay. Big background equals to this. Now we're really modding hard. Nothing is real, everything is trial and error. And here we have what we want. Do you notice how this vector that I've just drawn is always tangent to these contours? Which is quite nice, right? So from here, it tries to escape. From here, it tries to self-insert. And here it just acts like some kind of ferromagnetic powder or filament. And so here as well. And here you kind of get to appreciate the power of this complex number library, because you're able to purely rulily obtain a vector from something that is picturesque mapping. So then, what do you think we want to do now? And what I think is a good idea is something resembling a pixel engine to make some lame screensaver where a bunch of particles, attract to this pole, detract from this pole, and so on. So let's attempt this. We have this. Once again, we can keep all this junk for now. Okay, here we go. So, as you can see now, each particle is being added to the pipeline with the correct position and velocity. And so all we have to do is define velocity vector for each particle, Vp, and you see it travels in a tangent vector. So every time you do an iteration, you have to recompute the following. So an iteration is done, stored. Okay, that's pretty good progress either way. We just have to make them readjust their fields. So we do the iteration, we set a new position, so now we have to, okay, let's do this. Shouldn't change anything. And then of course the scary transformation. And the n. Let's change to I. Okay, what did I just do? Okay. Okay, this n is tricky here. And look at that. Now we have particles following our field lines. And that's pretty cool. Here you go. There's our screensaver-esque particle engine. And you see they start at the origin and make their way into the so-called black hole. So let's give this 1,000 as a stress test. Set the frame rate to that. And there we go, there's our particle engine. And let's see what happens if we do this. They exit, okay. If we do this, they get stuck, okay. If we do this, so there we go, there is our ferromagnetic filaments, whatever you want to call them. By pushing down the mouse, I'm creating a bunch of new particles which get sucked into the pole or zero, whatever you want to call it. And of course, I'm not exactly sure what happened in the past 10-20 minutes or so. But so the next thing that we can do is remove all the garbage, set the frame rate really high, remove the decorations, let's remove this decoration, make it particles a little smaller. And now you have something resembling some kind of a particle engine, vector field, whatever you want to call it. Let's just remove this, call this line. Oh, how cute, make it even smaller. Maybe a 5. Okay, there we go. And here's our crowd pleaser particle engine screensaver with alpha trailing and all that bullshit using the complex numbers library. Okay, that's about it. Fuck it.